Okay, so we've studied comets, right? We've even managed to land on one. But what if we could take the next absolutely giant leap and actually capture one? What if we could park a visitor from the very edge of our solar system right here in our own cosmic backyard? I know. It sounds like something straight out of a sci-fi movie, but believe it or not, this isn't just a Hollywood plot. Real engineers and astronomers are seriously crunching the numbers on how to turn one of these cosmic wanderers into our permanent neighbor. So let's break it down. Is this actually possible?
So why? Why would we even attempt something so audacious, so crazy? It's because the payoff, the reward for having a comet basically on call, would be nothing short of revolutionary for humanity's future in space. Just think about it. It's like having an all-in-one gas station and hardware store in orbit. We could mine its water ice to create rocket fuel, making trips to Mars or beyond vastly cheaper. It would be a pristine, deep frozen laboratory, holding the secrets from the birth of our solar system, maybe even clues to how life started on Earth. And of course, it's a nearly limitless source of materials for building things in space. All right, so the rewards are huge. But, as you can probably guess, catching a comet isn't exactly a walk in the park. To really get why it's so hard, we need to understand what we're actually up against. So our target is basically a giant, fragile snowball made of ice, rock, and dust. And we know from missions like Rosetta that they can be structurally weak, almost like packed snow, which makes them really tricky to handle. But the real problem, the thing that makes this a monumental challenge, isn't what they're made of, it's how unbelievably fast they're moving. That's right. These cosmic icebergs are hurtling through space at tens of kilometers per second relative to us. To capture one, we have to slam on the brakes in a cosmic sense. We have to fight an incredible amount of momentum. In the world of orbital mechanics, everything, and I mean everything, comes down to a term called delta V. Think of it as the price you have to pay to change in orbit. For a super high-speed comet, the delta V needed to slow it down enough for capture is just enormous. It's far beyond what any of our current rockets can do. So the billion-dollar question is, how in the world do we pay that cosmic price? Okay, so we've got this massive delta V problem, but this is where things get really cool. Faced with this colossal challenge, scientists have come up with some truly brilliant, if mind-boggling solutions. All right, there are basically three big ideas on the table. The first one is the most elegant. You play a game of cosmic billiards. You use the gravity of planets like Jupiter and even Earth to do a series of flybys, gradually slowing the comet down over many, many years. The second idea is to use the comet against itself. You control the jets of gas that naturally erupt from its surface as it heats up, turning it into its own little engine. And the third option? Well, it's brute force. You attach powerful, super efficient engines right onto the comet and just push. But here's the kicker. No matter which method we choose, the energy we're talking about is just staggering. To pull this off, you'd need to apply a force equivalent to setting off multiple nuclear bombs. But, and this is key, you'd have to release that energy incredibly gently and precisely over decades to make sure you don't just shatter your fragile prize into a million pieces. So, we have a plan, or at least the beginnings of a few plans. But this brings us to what might be the biggest, most important question of all. Even if we figure out how to do this, should we? I mean, just look at this. The stakes could not possibly be higher. On one hand, you've got a priceless scientific treasure that could unlock the secrets of our own origins and fuel our expansion into the solar system. But on the other hand, a tiny miscalculation, just one wrong move, and you could accidentally turn that treasure into an impactor aimed right at your own planet. And a 1-kilometer comet hitting Earth wouldn't just be bad, it would be a global catastrophe. And it's not just the technical risks. There are these huge legal and ethical questions that right now we have absolutely no answers for. Like, who gets to own it? Space law says no country can claim a celestial body. So what about one you dragged across the solar system? Who's liable if it all goes pear-shaped? A project this big would demand a level of international cooperation and trust we've frankly never seen before. Okay, so given these absolutely massive risks of trying to lasso a fast-moving comet from the edge of the solar system, there's a much smarter, much safer way to start. Instead of going after one of those classic high-speed comets from the Oort cloud, we could target a dormant one that's already in an orbit kind of like ours. See, some near-Earth asteroids are actually thought to be extinct comets. Their relative speed to us is much, much lower, which means, you guessed it, the delta V required for capture is dramatically smaller. This makes the whole idea far safer and a much more achievable first step.
So where would we actually park this thing? Definitely not buzzing around over our heads in low Earth orbit. No way. The safest spot would be far, far away. We're talking about a stable, distant orbit around the moon, or maybe at a Lagrange point, which is kind of like a gravitational parking spot in space, where an object can just hang out with minimal effort. There, it would be safe, and so would we. When you take a step back and really look at the whole picture, capturing a comet would easily be one of the most ambitious, grandest engineering projects humanity has ever even dreamed up. And I think that's why this idea just won't go away. It's so compelling. It's not just about mining for resources or doing some amazing science. It really taps into something fundamental about us, that deep human drive to explore, to reach out, and to turn these distant cosmic wanderers into tools for our own discovery and growth. This whole idea represents a totally new chapter in our relationship with the cosmos, moving from just being passive observers to becoming active participants. But it demands a level of technology, cooperation, and, frankly, wisdom that we may not possess just yet. So the ultimate question really isn't just, could we do this? But are we, as a species, ready to cross that frontier?